Hey guys, Mr. Dow here again. Today we're going to be looking at simulating experiments and wrapping up some notes from section 4.3. There's three different methods for answering questions involving chance. The first, we can try to estimate the likelihood of a result by actually performing the experiment over and over and over, and then just calculate the relative frequency. The problem is, this takes too long, it could be very costly, we might just not have the time or the resources to do this. Well, we could then try developing a probability model and you find the theoretical answer. The issue here is we don't know probability well enough. We'll be talking about that next chapter, so we're going to have to hold off on that technique. The third technique, and what we're interested in today, is developing a procedure to imitate the experiment and simulate the number of repetitions for the experiment. What we're going to do here is assign outcomes such as rolling a die or flipping a coin to different events, and then just repeating that process of rolling a coin and seeing how that correlates. For instance, maybe I wanted to know the likelihood of two parents having a girl among their first four children. Well, I'm not going to take a couple, let them have four kids, and then count if they had a girl within those first four children, and then repeat that process over and over with different couples. Well, that would take a long time. Well, an easy way to simulate this is to just flip a coin or roll a die. If I flip the coin, I can let heads represent having a boy. I can let tails represent having a girl. I would flip a coin 4 times, record the sequence of heads and tails, and see how that correlates to having a girl or a boy. I could roll a die. I could let odd numbers be having a boy, even numbers be having a girl, and roll a die 4 times, record the 4 numbers, and see how that represents having a boy or a girl. So simulation is just the imitation of chance behavior. I decide the model, I lay out the parameters of the model, I assign the outcomes of rolling a die, getting a heads or a tails to represent real life situations, and then I just calculate relative frequencies. Let's toss a coin 10 times. And I want to know the likelihood of a run of at least 3 consecutive heads, so heads, heads, heads in a row out of those 10 tosses, or 3 tails in a row, tails, tails, tails in a row. I don't really feel like actually tossing the coin 10 times in a row. So what I can do is go to a random number generator. A random number generator can supply the following list of numbers, grouped in 5, just to make it easier on your eyes. Now each of these numbers represent whether I flip the heads or tails, and I can decide how I want the numbers to represent the flip of a coin. I could do 1 digit to simulate 1 toss of a coin, and I'm going to go ahead and let odd digits represent heads, even digits represent tails. So if I look at the first 10 numbers, 19223, 95034, just the first 10 numbers, that's representing my first run of 10 flips of a coin. Every time I see an odd digit, I have a heads. Every time I see an even digit, I represent a tails. I've done this 3 consecutive runs. My next set of 10, 05756, 28713, is my second trial of 10 coin flips. And then 96409, 12531, representing my third trial of coin flips. Well, that's going to correspond to the following. I'm looking for consecutive runs of 3 heads in a row or 3 tails in a row. If I see 3 odd numbers in a row, such as in the case of 3, 9, and 5, I have a run of 3 heads in a row within those first 10 numbers that represent the 10 flips. During the second set of 10 numbers, I see 575, which corresponds to heads, 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 and 628, 3 even numbers, that corresponds to tails, 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 and additionally I see 871, 3 odd numbers, that represents 3 heads. So I have another successful trial of 3 heads or 3 tails in a row. It doesn't matter that it happened multiple times within those 10 numbers. During the third run, 6, 4, and 0 represent tails, tails, tails. I have a third success. So far, out of my numbers, my 3 sets of 10, I am 3 for 3 in terms of success of getting 3 consecutive heads or 3 consecutive tails in a row. If I were to complete this for, say, 25 more repetitions, and let's just say 23 of the 25 times I have 3 or more heads or tails, I can calculate an estimated probability, 23 out of 25, or 92% of the time, I could get 3 heads or 3 tails in a row. If I were to continue this thousands of times through a long simulation, maybe I would find out the true probability. In this case, I'll give you the heads up on this, no pun intended. It's 82.6% chance of me getting 3 heads or 3 tails in a row. Well, only continuing this for 3 trials, I get 3 for 3, 100%. The more trials I continue, the more accurate representation I'll get to the true probability of 3 consecutive heads or 3 consecutive tails in a row. What if it's not a 50-50 chance, like heads or tails? Suppose I have a quarterback that completes at a 70% pass completion rate. Well, I'm going to simulate 25 passes to represent 1 football game. If it's 70%, rounding to the nearest tens, I can let the digits 0 through 6 represent he completed the pass. There are 70% of the numbers from 0 through 6, keep in mind 0 is a number, representing complete. If a number 7 or 9 comes up, I would say, well, then that was an incomplete. I could do a similar series of events where I list out 25 numbers in a row, count how many 0s through 6s I have, denote them as completions, count out how many 7, 8s, or 9s I have, denote them as incomplete. Again, 0 through 6 is 70%. Keep in mind, 0, 1, 2, 3, 4, 5, 6 is 7 numbers, giving me the 70%. What if I'm not rounding to the nearest tens? So let's say I'm working at a yogurt store or a frozen yogurt store, and the relative frequency of people that prefer chocolate, vanilla, and strawberry are given as below. I want to run a simulation where I'm picking 2-digit numbers to represent chocolate, 2-digit numbers to represent vanilla, 2-digit numbers to represent strawberry. I cannot use single digits in this setting. I'm going to have to choose the numbers 00 through 99, where the numbers 00 to 37 represent chocolate. Keep in mind there are 38 numbers from 00 to 37. The numbers for 42% and numbers for 20% will follow sequentially in order to give me the numbers from 00 through 99. Let me go ahead and give you a string of 20 numbers. The first 2 digits represent the ice cream or frozen yogurt preference. 19 corresponds to chocolate. I define chocolate as 00 to 37. So I have one person preferring chocolate. The second 2-digit numbers, 32, also represent chocolate, which is defined from 00 to 37. I can look at all of these 2-digit numbers in a row to formulate how many people prefer chocolate and how many people prefer strawberry. So out of my run of 20 numbers, I'm simulating 10 different customers. Each 2-digit number represents a different customer. Only one time did I have a person through simulation preferring vanilla, which is when I had the 57. So I could say one time out of 10, I would have a customer preferring vanilla. Well, my simulation found 10%, where my relative frequency was 20%. That's not too far off. Here's another scenario when I can assign digits. Let's say I'm interested in having children, but I want to continue having children until I finally have a girl. Let's say having a girl would be a success. Maybe I have to have 3 boys in a row, and then finally I could have a girl. Maybe I can have a girl on my first child, and I can stop there. Well, I don't want to actually carry out the experiment of just having children until I have girls. So I'm going to let numbers represent boys and girls and look at a series of numbers to see how long it takes until I get my first girl. Let's take a look at the following set of numbers. Again, grouped in 5 just to make it easier on your eyes. This model is the same as coin tossing. Each child has a probability of 0.5 of being a girl and 0.5 of being a boy. The sexes of successive children are also independent. Assigning digits is also easy. I'm going to let one digit simulate the sex of one child. 0, 1, 2, 3, 4 will represent a girl. 5, 6, 7, 8, 9 will represent a boy. The first three numbers that I occur, 6 represents a boy, 9 represents a boy, and 0 represents a boy. Excuse me, I misspoke there. 0 represents having a girl. Well, according to my numbers, 0 through 4, representing a girl, once I get my first girl, I stop. So I had 3 children before I had my first success, a girl. I then look at the next 2-digit numbers. 5 representing a boy, 5 through 9 representing boys, 1 representing a girl. I had a girl within 2 children. I look at the next set of 2 numbers. 6 represents a boy, 4 represents a girl. I stop. And I could continue this out to see how often I have a girl within 3 children, or my first 3 children, within my first 4 children, or on the first child, as in the case when I got the 0 and I got a girl right away. If you don't like using random generators on the table in the back of the book, you can also use your calculator to run these simulations. We simply select Math, over to PRB, option 5, Random Integer. I'm going to select the numbers from 0 through 9, and then how many numbers do I want? In this case, it would be a string of 5. The calculator will output to me 5 numbers that could represent having a boy, having a girl, ice cream, completing a pass, not completing a pass. The basic steps to simulation are as follows. State the problem or describe the experiment. State your assumptions. Assign digits to represent outcomes. Simulate many repetitions. State your conclusions. Next, I'd like to just highlight a few featured items from section 4.3 when designing studies. These notes should follow along fairly close to your text if you wish to follow along with me. Let's look at the scope of inference. The key difference between experiments and observational studies is observational studies don't always show a cause and effect relationship. They may show a correlation. Keep in mind, correlation does not imply causation. 2 items might have a relationship with each other, but one might not cause the other. An experiment can point that out. The treatment can cause a change. Here are some other key bullet points detailing were individuals randomly assigned to groups, yes or no, and were individuals randomly selected, yes or no. There are a few challenges of establishing causation. Well-designed experiment tells us that changes in the explanatory variable can cause changes in the response variable. We might have a lack of realism, or in some cases it might not be practical or ethical to do this experiment. But it is sometimes possible to build a strong case for causation in the absence of experiments by considering data from observational studies. If not performing an experiment, here's a few different things to note for trying to establish this causation. Just a few key bullet points. If we do have a strong association, it may be possible to establish causation. Or if the association is consistent. And just a few more for you. We talked in class about the ethics and morality of running experiments on people. Here are a few guidelines to think of. So just tying up a few loose ends here from 4.3 in summation. Inference about the population requires that individuals taking part in a study be randomly selected from the larger population. We're trying to look for that cause and effect relationship. We might have a lack of realism in experiments, especially when doing simulation. And studies involving humans must be screened in advance by an institutional review board. We want to make sure the participants give their informed consent and our results kept confidential.